We'll start Chapter 17 with an overview of pulmonary circulation and then look at diffusion of gases. Remember that respiration involves pulmonary ventilation or breathing, which we talked about in the last chapter, and it also involves gas exchange between the lungs and blood, transporting the gas in the blood, and then gas exchange between the blood and the tissues. So that's what we're going to be covering in this chapter. And then just a reminder, why do we need oxygen? So remember, we need oxygen for the mitochondria to be able to make ATP. And then carbon dioxide, the waste product, remember that comes from breaking down your food. So the carbon in your food, as you break it down to release the energy to make ATP, the carbon from the food becomes carbon dioxide, which we exhale. What I want you to get from this picture is that whatever the tissues are doing, however much oxygen they're consuming and carbon dioxide they're producing, the lungs have to keep up with that. So whatever exchange rate is going on in the tissues, the lungs have to match that in order to keep the tissues supplied. The air we're breathing in is actually a mixture of gases. 79% of the air is nitrogen gas, and then 21% of the air we're breathing in is oxygen. The water is going to vary with the humidity, and carbon dioxide is the smallest percentage at 0.03%. The atmospheric pressure of the gases outside of our body that we're breathing in is just the combined pressure of all of these gases. So this is where Dalton's law comes in. So make sure you know Dalton's law. This is really important. So Dalton's law just says that the total pressure of a gas mixture is equal to the sum of the partial pressures exerted by each gas. So here's how Dalton's law works. So let's say that we're at sea level and the atmospheric pressure is 760 millimeters of mercury. And let's say that there's no humidity. So we're just going to look at the partial pressure of nitrogen, oxygen, and carbon dioxide. So to figure out the partial pressure of each gas, we just take the percentage of the gas mixture that, for example, is nitrogen gas is 79%, and then we multiply that by the total atmospheric pressure. So out of the total atmospheric pressure of 760 millimeters of mercury, 600 of those millimeters of mercury are due to the partial pressure of nitrogen. And then oxygen, 21% times the 760 would equal 160 millimeters of mercury. And then if we take a look when the air has 100% humidity, and the reason we want to look at that is that's because that's the amount of humidity that's inside the alveoli, because there's a thin layer of water inside there, and so there's 100% humidity down in the alveoli. So if we look at the percentages of the gas mixture when the gases get down into the lungs, notice that the nitrogen goes from 79% to 74.1%. And that's because there has to be room for the water vapor. So that's taking up some room, and so there can't be as much nitrogen in the mixture. And then the same thing for oxygen. There's 19.6% oxygen in the gas mixture in the alveoli compared to 21% that's out in the air outside of our body that we're breathing in. So the partial pressure of oxygen down in the alveoli decreases to 149 millimeters of mercury, whereas the air that we're breathing in, if we don't have any humidity out there, it's 160 millimeters of mercury. Just to give you another example of how Dalton's law works, if you hike up to 14,000 feet, the atmospheric pressure at that elevation is only 440 millimeters of mercury, so it's no longer 760. So if you're breathing in 21% oxygen and you multiply that by 440, the partial pressure of oxygen is 92 millimeters of mercury. And that's a lot less than if you were at sea level at 760 millimeters of mercury. The partial pressure of oxygen is 160. So you can see why when you're at 14,000 feet, you're gasping for air, and your muscles get fatigued very quickly because there's not as much oxygen in the air that you're breathing at that high altitude. Gases are going to diffuse down their partial pressure gradients, so they're just going to go from high to low pressure. And what's really nice is that they ignore any of the other gases, so they just look at their own partial pressure gradient. So you can see, for example, the partial pressure of oxygen in the alveolus is 100, and then in the pulmonary artery, which remember is bringing the deoxygenated blood into the lungs, the partial pressure is 40. So oxygen is just going to diffuse down its partial pressure gradient from the lungs into the blood. And then the partial pressure of carbon dioxide is much higher in the pulmonary artery because that blood is coming back from the body and has picked up the carbon dioxide waste from the tissues. And then the air that you're breathing in, the partial pressure of carbon dioxide is only 40. So carbon dioxide is just going to diffuse down its partial pressure gradient, moving from the blood into the lungs. Henry's law is another really important law that you need to know besides Dalton's law. Henry's law is important because the carbon dioxide and oxygen are going to be dissolved in the blood. And Henry's law just states that gases can dissolve in liquids depending on their solubility in the liquid and their partial pressure. So the greater the solubility and the greater the partial pressure of the gas, the more the gas is going to dissolve in the liquid. And if we take a look at carbon dioxide and oxygen, neither one really likes to dissolve in the blood. Neither one is very soluble. But if you compare the carbon dioxide and the oxygen, carbon dioxide is 20 times more soluble in the blood than oxygen is. A good example of Henry's law would be a can of Coke. So it's a carbonated drink, and what they do during manufacture is they put the carbon dioxide under high pressure, and the higher the partial pressure of the gas, the more will dissolve into the liquid. And that's how they get the carbon dioxide into the Coke can and dissolve in the Coke. But when you open up the Coke can, the carbon dioxide doesn't really like to be dissolved in the Coke, so it will escape, and then after a little while your drink will go flat because all the carbon dioxide has left the Coke. So here's an example showing you the solubility of oxygen. So the partial pressure of oxygen is 100 millimeters of mercury, and we're going to start off with no oxygen in the water, and then the oxygen molecules are going to diffuse across until the partial pressures are equal. And if you look at the concentration of oxygen in the water, it's only 0.15 millimoles per liter. And then if you take a look at carbon dioxide, and if we have carbon dioxide at the same partial pressure, notice that the concentration of carbon dioxide is 3 millimoles per liter. So you can see that a lot more carbon dioxide will dissolve in the liquid than the oxygen will. So carbon dioxide is 20 times more soluble than the oxygen in the blood. And that means that we can't dissolve very much oxygen in the blood. So in order to get enough oxygen in our blood and carry it to our tissues, that's why we evolved hemoglobin, to carry the oxygen in the blood for us, because very little oxygen likes to stay dissolved in the blood.